Good morning. My name is William Schwartz. I'm going to present this work, smart surveillance, data representation, and scalability issues. The idea is to give you an overview on what is smart surveillance, a little bit of what is biometrics, and some problems we face when we try to have it in a real world. Just a second here. Okay. So I'm from University of Federal University of Minas Gerais. It stays in Brazil, and at this place here in the center, in the southeastern part of the country. It has about 30,000 undergraduate students, 8,000 graduate students, so it's a reasonable big university, and about 3,000 faculty members. I'm joined in the computer science department in 2012. It has 65 faculty members. It has two graduate programs, one master's, one PhD, and it has the CAP is grade 7, which is the highest in the country. There are 7 programs on this grade these days. This is the internal part of the institute. Here's the entrance, and here's our new building. So we moved to this new building in 2016, end of early 2016. It's a brand new building with space for laboratories. And one of them is this. That's my research group, a smart surveillance interest group. So basically we work on surveillance and biometrics and try to solve large-scale problems. We have 1 postdoc student, 11 PhD, 3 masters, and 8 undergrads. So you can have a little tour for inside the lab. So, smart surveillance. What is the difference? What's the difference between surveillance, as we know usually, and smart surveillance? If you're doing surveillance, you see many cameras everywhere, but that's not smart surveillance because it's not processing the data. It's only collecting the data, saving in some storage server, and then somebody has to go there and watch if some event occurs. Smart surveillance is different. You collect the data, you save the data, but also you process the data and try to inform the operators of the system as the event happens. So you are proactive in the process. So what are the goals? We want to analyze the activities that are being developed in the scene. So we want to understand what's happening in the scene. For example, I want to know if there is something suspicious happening or something out of usual is taking place in some cameras. The idea is not to make automatic decisions. I don't want to man a robot and kill the person that is doing something wrong. I want to alert the operators of the system to make sure that what we think is important is really important in the surveillance system point of view. So we're trying to basically filter the information. Imagine you have 50 cameras and you cannot have people sitting there and analyzing all these cameras. So you want to filter this information, and you have few people looking at this filtered information to make sure that the environment is safe. That will help preventing criminal activity. It is going to give you high-level information to the operators. There is a relation between surveillance and forensics. You can see one, you can link both, because surveillance tries to predict some action, And forensics tries to, once something happened, try to find evidences to find the suspect and to incriminate the suspect. So we can see there is a point here, which is the event. So if you're doing surveillance, you don't know what is the activity. You're trying to predict what activity is going to hurt somebody. So you don't know the activity, you have to search for suspicious behavior. Once the event happens, so you know what happened. So you're starting in the computer forensic side. So you know what happened, then you go back in the data, try to find why that happens, who was involved, to find the suspects and the collaborators of the perpetrator. So, but you can use the same techniques as you use in surveillance, you can use in forensics. For example, if you want to track somebody, you can track online as the videos are being collected in real time. Also, you can track backwards. You can, okay, the event happened now, here, at this point, so track back to find something, the people who the perpetrator talked to find collaborations. So you can use basically the same techniques in both. Here I will talk about the techniques, not much on the if it's forensics or surveillance, but you can use in both sides. The difference is one is doing in real time, which is very hard. Another one is doing offline. You can say, but today I can find an object detector that runs at 150 frames per second. Okay, so do that, track the people. Now, once you detect the person, you have to track that person. Not only one camera, but I don't know, 70 cameras, 100 cameras. How do you do this? Even if you have a large computational infrastructure, it's very hard to solve this problem. You cannot solve it independently. You have to look in one camera and try to see if the person that walked in that camera is in another one afterwards. So it's a dependent problem. It's very hard to do this in real time. So that's one of the big challenge we have, the scalability of the methods. So, what's the problem these days? We have, I call here, plenty of eyes. We have many cameras. For example, city of São Paulo has 1.5 million cameras. They're not state cameras. They are cameras everywhere, from private companies for the police, but they're not integrated. But if they were, how do you process this data? You see all the time some footage from surveillance cameras, but always after something happened, never before, never while it's happening. So we have many cameras. The connectivity is very high, and also the quality of these cameras is very good. For example, look at this camera. It's getting a wide view, then it's going to zoom, and basically you can read what's in the ship from 300 meters or more. So the quality, it's good. So the problem is, what about the brains? So you have all the data, you're collecting all the data all the time, but how do you process that? So you have to, since you have lots of data, you have to monitor that data. You have to process that data real time to be able to understand what's happening. So plenty of eyes. What about brains? There is a lot of research on the area. So this is a chart. It's a little old. It's 2014 when we stopped collecting these trends. But you can see after, this is the number of publications in IEEE involving surveillance. So you can see a boom after 2001, of course. And it's increasing. So there are many publications on this area. If you pick one single problem, for example, if you pick face recognition, I just searched this. I searched the 2016, early 2016, and this I searched early 2017. So you find 127,000 reference to face recognition if you search for the term in Google Scholar. So there are a lot of research being done on these subjects. Face recognition is just one of the problems involved in video surveillance. You want to identify the persons involved. But the main problems are, basically, I want to do this. Where is Wally? I don't know who is doing something wrong. I need to identify this person. But not only that, I also want to, who is it? Who is Wally? I want to, that person is doing something suspicious or something out of normal. Should I look it more carefully or just, okay, it's just running in this place because it's late for the bus? I need to know who this person is, because if the person has a record, I should pay attention. What's the person is doing? Is that suspicious or is just a regular activity? With whom? Who is doing that with that person? Is a group activity or a single person activity? That changes the high level information that you can get from the scene. And when that's taking place. That's very important, but everything has to be in the real world. For example, these two cases here. So you want to be able to solve these problems in these kinds of scenarios, which are very hard. That's why there are many papers published on these topics, if you pick them separately, but no paper is able to work on in these scenarios. So they are advancing, but still not at level that you can use in a real scenarios. For example, in a metro station where something may happen there. If you don't have robust and scalable methods, you cannot do anything. So that's the overview of surveillance. Now I'm going to give you an overview on biometrics. So what is biometrics? It's the science to establish the identity of one individual based on some physical or chemical or behavior trait. It's different from what we do when we want to log in a system where you type a password. Password is something you know. Biometrics, something you are. So if it's something you know, somebody can borrow, can copy from you. But if it's something you are, nobody can copy, or it's depending on the trait you're using, it's very hard to copy that information. For example, fingerprint, 10-finger fingerprint. It's very hard to copy that information unless you're doing some kind of spoofing. So it's something that is yours. The problem of it is you just have one, or 10 fingers, you have the 10 fingers. If somebody steal that, you cannot change it. That's the whole point of biometrics. You don't change it. For example, iris. If somebody can copy that information, then you cannot change your iris, the information of your iris. So it's very hard to. So we need to work very hard to protect that information, to protect the templates extracted from many biometrical traits, because once it's stolen, then you are in trouble. There are many types. You can see here many types of biometrics. For example, palm print, fingerprint, 10-finger fingerprint, iris, faces. So which one to pick from? Every day we find another new biometric. For example, this one, the kneecap, is a biometric. You can use that to identify a person. But how convenient is that? Can you imagine you going through the security in the airport, have to raise your pants and, okay, that's me. I have to take a picture, do an MRI while in the line. So it's a trade-off. So we have very good biometric traits, for example, DNA, but it's very hard to collect. So there is a trade-off between the accuracy of the trait and the censoring of that trait. And that's this plot here. In this axis, in this axis here is the accuracy. You see DNA is very high. And this axis here shows the distance that the range you can collect that information. So you see DNA is almost zero because you have to have the collaboration of the person to collect that information. You have to sample blood or something from the person to be able to collect the trait. Other information, for example, face. Face is not on the orange, it's more towards the right. So more right here, you can censor from more distant. But once you collect here, the face, it doesn't have a very high accuracy. So you can collect from a distance, but the accuracy is not good. So the goal is try to find some biometric trait that you are here and here. So you can collect it from a distance, but also you have very high accuracy. Unfortunately, that's not available yet. There are some biometrics that you can collect it from distance, but the accuracy is very, very low. So we want to find something that is in this region, mainly to surveillance, because you don't have cameras. The camera is not with the person. The camera is in the environment, and the person is passing through the cameras, and you need to be able to collect some data to identify that person. It's very hard problem. Faces getting better and better every day. But still, if you see a Facebook picture, you have papers saying, okay, you get 100% of accuracy. Yes, on that type of pictures. But if you see surveillance pictures, they are very different. They're taken from the top. You get the head, a lot of the head, not much of the face. From 100 meters, from 50 meters, you have blur, you have an interference of the environment. So it's okay, almost solved for the pictures we take when the person is collaborating with the picture. But in a surveillance scenario, people don't want to collaborate. People who collaborate, okay, they're harmless, but who is trying to hide from the surveillance system? These are the people we want to identify, and they are not going to collaborate. They are not going to look at the camera. So we have to find some other way of collecting that information. So what's involved in biometrics? So we can see 4 modules in a biometric system. Sensor, which is how you collect the trait, the biometric trait. The quality assessment. So once you collect the data, you have to check the quality of that data to see if it's worth going ahead. For example, you take a picture and you just get a blurred face. It's useless. So you have to take another picture. So this is assuming that you're in a collaborative system. You want to collaborate with the system to identify you. For example, in Brazil, now we have the biometric of the fingerprint to go to the elections. Before you vote, instead of you sign, you put your finger there. And in these cases, you want to collaborate with the system. So you have this quality assessment. If it's okay, then it is go to the matching process. So what is I'll talk more about the matching later. And then you have a database where you have the templates previously collected. For example, if you register for voting, what they're going to do is they're going to collect your information, they're going to collect your fingerprints, it's stored in a database. And then when you go to vote, you collect again, they're going to see this person possesses the same information that was collected in the first place. Because in the first place, when you go to to register for voting, you go with your documents. There is a person there saying, yes, you are you. So the person is attesting that you are actually the person who owns that document. So it's a safe collection. Then you go there, collect your fingerprints. In the election, there is no person to attest that you are going to attest that by your fingerprint. So you go there, put your fingerprint, it matches, okay, you're who you are. Then you go and you vote. That's the part of the matching. There are two important tasks on biometrics. So you always, when you read papers, you're always going to see these two tasks. If you go to the real world, it's almost always the same. The first task is being done, which is verification. What's the verification? You are claiming some identity. So basically you're saying, okay, I am the person who owns this badge or who owns this ID. Your ID has your template, your biometric information stored on it, or it is able to access a database which has your information. Only your information is on your card. So you collect your biometric trait, then it compares, it does the match, say, okay, the claim identity is valid. So you're the correct person or you're imposter. You're not the person you claim you are. So this is verification. For all biometrics, you can use just these two tasks. So fingerprint, face, iris, you can use these two tasks here. The second task is identification. This is different. They have a large data set, database with all known persons that went there, collected the data from those people. They're storing the data set in the database. Then you go there, take a picture, don't say anything. It's going to say, okay, you are in this database and your identity is this. So you can see here, you have in the matching for verification, you just have 1-to-1. So we call it, hello? We call it one-to-one problem matching. And here, face identification, biometric identification, you have one that is, you just collected the data, and you have many known subjects that are enrolled on that database. It's very hard problem because to be able to encounter your true identity, you have to be right for each one of the others. So that is a very tough problem. So, given the introductions of the two areas, the surveillance and biometrics, now I'm going to present some issues and some works we've been done on these areas to handle the problems of scalability. So how to be able to handle many people in the system, how to handle many cameras, how to cover the environment. How can I, with 2 cameras, how can I cover this room? I don't want to have everybody in view. If I have everybody in view all the time, I cannot get details of anybody. So I have to have 1 camera that gets the entire view, and other cameras that zoom to the faces of the people to get details when I need. So it's a hard problem because you're not able to have 100 cameras in one room to be able to get everybody's face. So you have a few cameras because it's costly. And you have to create methods to control these cameras so that you can zoom in a person when you need. So everything has to be in real time. Because if the person is moving, you zoom, and the person already left, you miss it. So you have to predict the movement of the person, and again, everything in real time. And the data representation, it's another problem. How to encode the information. You have pictures, you have videos. So for pictures, it's easy. that's almost solved with deep learning. You just pick your get your picture, present to the network, and it's going to say, okay, there is a person there, there is this object there, there is the other object there. But for videos, this is not solved yet. First, how do you combine the multiple frames? You just stack them, the dimensionality of the data increases. But look that you're dealing with two different informations. If you're looking into just single frames, you have the spatial information, which is the width and height of the image. They are given in pixels. But if you incorporate the time, you have three dimensions. You have the spatial information and you have the temporal information. You cannot pick all this information and put in a pack and try to process as if it was a volume. It doesn't work like that, because it depends on the frame rate, it depends on how fast the video is being collected, how many frames you have there, the window you collected from the data, because you cannot put the entire video to a network. That wouldn't work because it's too many parameters. So it's still an open issue. We have some works on this. The community is working on this, but it's still not solved. So for the first, for the scalability, I'll talk about two works we did on face recognition and to try to be faster when we're doing face recognition. We work on the task of face identification. And for the data representation, I'll talk about activity recognition and anomaly detection. Activity recognition is basically, I want to know what you're doing and I know what I'm looking for. Right? When you have activity recognition, you already know the activities you are looking for. I want to know if the person is eating, the person is walking, the person is running, the person is talking to somebody. I know beforehand what the activities are. On the other hand, the anomaly detection, I don't know what I don't know the name of activities because they are anomalous activities. So they are activities that don't take place every time. So I know what is regular, and everything that is not regular, which is not expected, I call anomalous. So that's the difference between these two problems. The first one is a classification problem that I have the classes beforehand, and the second one, it's a one-class classification problem. I just know what is normal, but everything else I don't know. If something takes place, I have to emit alarm. So this, so let's start by the face recognition. So these are two papers, one neurocomputing and one IJCB this year. The first one, they're similar in the sense that they try to do create random models to be able to identify people. So specifically in face recognition, we have the same tasks I mentioned before. So if you're doing face verification, you're trying to see are these two face samples from the same person or not. You show two pictures, and the system will going to say, yes, they are the same, they are not the same. The user is valid or it's an imposter. So that's the task on face verification. Identification is, as I mentioned before, you have a gallery with many known subjects, and you have a new face image. You're going to say, okay, what's the identity of this person given this gallery of known people? Then there is the open set. The last one is the open set, which is more realistic because if I get one new picture of a face and I have a gallery of known people, the first thing I need to know is this new person, is this new picture anybody of the previous known gallery? If it's not, I discard because I say that's not the person I'm trying to identify. These open set identification problems, they are very useful. For example, when you have a list of suspects, a list of people that are wanted, for example, in the airport, you have thousands of people walking there every day, but you don't want to identify every one of them when they're walking. You just want to search those people that are suspicious from something. So you have the list, so you have this gallery, previously known. Then for each person that you take a picture, the first thing is this person in this list or not? If it's not in the list, that's not a person of interest, so you don't do anything. If it's in the list, who is this person? Then you try to identify. So basically this last problem is a combination of identification with a detection. You detect if the person is wanted. If so, who is the person? So the first work try to handle the identification problems to increase the scalability of the system. Here is the traditional pipeline of face identification. Basically what we have, you have very many subjects that you know, you have n subjects there. You build one model for each subject, and to see the differences between this subject to all the others, basically you set the subject A in this case as a positive class in the classifier, everybody else as a negative class. So what you do here is your feature extraction and your classifier, they are going to emphasize those features that distinguish subject A from the remaining subjects. Then if you have n models, you will have, if you have n subjects, you will have n models. In the testing time, when you present a new face that you don't know the identity, you're going to present this new face to each one of the models, and you're going to have a response. Which one is this face is more similar? Remember that here we are not working on the open set task. So if I present a face to the system, I know that this face is in the gallery. I don't know the name of the face, only that. So once I project this face into all the models, one of them is going to give a high response saying, okay, the features of this new person that you're presenting are very similar to this person in the gallery. So it should be the best match. The identity is that. In this case, the highest response. The problem is, for every new picture I have here, I have to project this picture in all the n models, and that's very costly. So how do you reduce this cost? So we proposed a filtering stage where you, instead of you projecting the features from the testing subject in all the models, first you project this picture in the features of this image in a auxiliary set of models that doesn't depend on the number of individuals in the gallery. Then you have a rank to say, okay, this is more similar to subject A, this is more similar to subject B. You sort this list, you rank this list, and just analyze in depth those subjects that have high scores. So basically you're adding a new layer here, but this filtering is very fast. We did some way of doing in binary matching, which is much faster than projecting on these very expensive models. For that, we use the local sensitive hashing, which is a way of, you have your feature space, you have the points in the feature space. And the local sensitive hashing, it allows you to project that information in a new subspace, very low dimensional, and that new subspace, the points that are close in the initial subspace, they are still close in the new subspace. So it's a projection that you guarantee that who is similar in the original space is still similar in the new space. And in this new space, you can compare very fast. So here is just an example how the intuition of LSH. So you have a random projection here. You have your points in this space. So you have 2 dimensions here. Then you project every point of your original feature space in this new projection vector. You are going to have a space like this. If you keep adding new projections, so the second projection with beta, then you have a 2D space where the points that were close here, they're still close there. So this is doing randomly. You have random projections. If you keep doing this, you approximate, the more projections you have, you approximate the original distances in the original space. So, but this is doing randomly. We don't want to do randomly this. We try to incorporate a little bit of discriminability on that, because we have the identities of the people. The only thing we don't want to be is we don't want to test n models. We want to test a subset of n models. But we can use this information to build these projections in a better way. So we use this method called partial least squares, which is similar to ordinary least squares, but instead of performing the regression in the original subspace, in the original feature space, first it reduces the dimensionality, then it performs the regression, and this is better because you avoid instability, numerical instabilities in the process when you have a full rank when you don't have a full ranking matrix, which is usually the case with images because you have a lot of redundancy on the data and you cannot invert your matrices. So this PLS enables you to project it, to create a subspace that you guarantee that you have full rank matrices, and then you apply regular least squares. So here is a comparison between, the colors are not good, but when you do PCA, principal component analysis, that doesn't depend on the data labels. They just depend on the distribution of the data in the space. But we want to classify in 2 classes, the red and blue. You see that there is mixed on circles and squares here. When you apply PLS, you have a better discrimination. You can see the red circles to this direction and blue squares to this direction. You can almost find a linear separation between them. So it's adding on these projections that LSH does randomly, it's adding discriminability. So you don't need to have too many models. So what we do? So we have subjects of, we have subsets of subjects. We have the gallery. For example, here we have 4 individuals. We split randomly in 2 classes, the positive set, the negative set, and build a PLS model. So what it's going to do is create a projection that separates individuals A, C from individuals B, D. So this is one model. And we keep doing this. But when we do, every time we do, we change the distribution of positive and negative. Basically, we get the gallery, split in 2, and build a new model. See that this is not related to the number of subjects. You choose the number of models you want. Then in the test phase, so you have a bunch of these models here. You have n PLS models, where n is much smaller than the number of subjects. You repeat this process n times, so you're going to get n models, where n is much smaller than the number of individuals in the gallery. And then, when you have a test image, you project these features on all these n models. What is going to happen? It's going to say, if this test person is subject A, it's going to, when the subject A is in the positive model, the classifier is going to say it's a positive class. When the subject A is in the negative model, the classifier is going to say it's a negative subject, it's in the negative class. So you keep doing this. If for the correct person, since you did this in a random, the splits are random, the likelihood of get a sample from subject B and follow the same path, meaning hits the positive class, negative class, positive class, positive class, as a random subject is very, very unlikely to happen. But it's very likely that the projections are going to follow the same path as you have in the correct subject. So you're going to get a high response for the subjects that are similar to the test sample, and a low response for the subjects that are different from the test sample. Then you can just sort this list. You sort this list, get a few percentage of this list, and use that to perform your actually face identification in the models that are very expensive to compute. To evaluate this, we use this curve called MAR. It's maximum achievable recognition rate. What that is. Note that when you're doing this filtering, if you don't add the correct subject in the short list, you're going to miss. You're not going to be able to classify it later because you already removed that subject. So what we do, we have this plot here to evaluate how well our filtering process is. This goes in the y-axis from 0 to 1. If it's close to 1, means that, okay, the correct subject, the actual individual was selected in the short list. It was filtered and is in the short list. The farther you get from 1, meaning that you didn't select everybody. 0.1 means you select only 10% of the correct subjects. That means your identification rate will be at most 10%. And this axis shows the percentage of subjects in the candidate list. So once I increase this number because I allow more people to be in this short list. But remember, if you put more people in this short list, your identification stage will be slower because you have to test more models. So ideally, you want to be very close here. For example, here is 1%. So you're selecting 1% of the subject list from the gallery. Ideally, you would get 1. So you never miss the correct guy to pass to identification. So we did some evaluation in the number of hash functions, the number of functions we built. We see that once you increase the number of functions, the MAR increases. Basically, if you have more hash functions, you approximate better the distances, then you have a better chance of creating a list with the correct subjects. But after a while, it doesn't increase much. So we stopped at 200. 200 hash functions, you stop and you build only 200, then you apply that models. Basically, you have for each face test image, you have to project in 200 models. It may be large if you're working small data sets, but this day, that is data sets with thousands of subjects. So instead of projecting your samples, your features in thousands of models, you're projecting 200 models, and then you're doing identification just for a few percentage of those 1,000 subjects. So that's where the scalability comes from. And here are the results in the ferret data set. Is an old data set with 1,200 subjects. Here is the results achieved with the brute force method. Basically, is the first pipeline I showed. You just test everybody. So these are the results. The higher, the better. And these are the results with the filtering. So here we see that filtering 3% of the candidates, basically we just analyze 3% of the individuals in the gallery, we already get the results very similar to doing the full search. So, and this shows the scalability of the method. So we don't need, with just 3% of the candidates of the gallery, we are able to recognize everybody. Oh, recognize everybody, no. We are able to get the same recognition rates we had with the full pipeline of the method. Then, based on this idea, we extended this idea to OpenSet. So basically OpenSet, as I mentioned before, we want to know if that's a person of interest. Is it in the gallery or not? So what is our hypothesis here? So we still keep the idea of the classifiers, it's the same idea, and we split, for each classifier, we pick the gallery subjects, split in two, half and half, we build a classifier. We keep doing this m times. The hypothesis is what's the chance of two faces being in the same classes for m classifiers? Basically, it's the same as saying you have two random binary strings. What's the chance of the two are the same? So the more classifiers you have, this chance reduces. The more bits you have in this string, the chance of two random strings being the same reduces. So here is the same. Here follows this idea. If you pick your gallery, and then you have an individual that is not in the gallery, what is the chance of this individual follow the path, for example, of individual A, being positive, negative, positive, or individual E, positive, positive, negative? It's very, very unlikely that happens. So we expected some response like this. If the subject's known, it's similar to somebody that if the subject is in the gallery, you're going to have a peak. Basically what I'm doing here, we get the responses of all classifiers and integrate in a histogram. Each classifier votes for half of the subjects as positive, half of the subjects as negative. So if the face that you're presenting to the system is from somebody in the gallery, you're expecting a peak here. If the face is from somebody else, it's not in the gallery, the chance of following the path to get to the same positive, negative classes is very unlikely. So we expect a response like this. It's uniform, not really uniform, but it's more spread on the beans. So it could be anybody of the gallery. So that's the way we do this, the decision on if the person is in the gallery or not. Here is one example. So we have these m classifiers. To build them, you split all your subjects in positive and negatives, build n classifiers, then you have a probe sample, a test sample, you classify in each one of them. According to the responses, you increase this histogram, and then you have a threshold. If the maximum response is higher than a threshold, you say, okay, we are in this case here, and this subject is in the gallery. Otherwise, if there is no single being that is higher than a threshold, we are not in the person is not in the gallery. So here we have some results. First, we have to find the threshold, to define what is the threshold. It's not enough just higher than 20 is good, because it depends on the number of models you have. So you have to have a relative classifier. So what we test is, the first test is the score of the first divided by the score of the second. Another approach was the score of the first divided by the score of the second plus the third on average. And we test these strategies. We saw that these two first strategies, the first is the first strategy, the threshold one, is dividing the response from the first, the highest, with the second highest and third highest. The second threshold is the highest over the second highest. Basically, these two approaches, you can see here is the ROC curve. On the y-axis, you have a true positive rate. The x-axis, you have false positive rate. So the higher you're here and the closer you are to 1, 0 is better, because the true positive rate means that you everybody that is in the gallery, you're saying that is in the gallery. The false positive rate is you're saying that one person is in the gallery, but actually it isn't. So you want to be close to 0 in this axis, and close to 1 in this axis here. So we summarize this curve by the area underneath it. Close to 1, the better. So we get in the threshold 1 and threshold 2, 0.96, and use these two strategies to consider as threshold. The third strategy, we divided the highest response with a percentage of the second, third, and others, and did it work well. So we fixed on these two first thresholds. And here some comparisons considering the area under the curve. These are methods from the literature. You see they reach about 0.86, and our proposed one version of our proposal reached 0.91. It increases the results, and is significant, statistical significant, this result. I'm not going into details because of the time, but we test handcraft features and also deep learning based features. And so the hog here is handcrafted, and VGG is deep learning based features. So that is for the face recognition and the scalability. So with that, we are able to reduce the cost to process many faces in the gallery. So the second issue is data representation. So we want to be able to use the visual information, temporal information, to get better representations to pass to CNN or to directly classify if you're doing activity recognition. So the first part is the anomaly detection. So the first question is, what anomaly? What is anomalous? Is this anomalous? It depends on the context. Is this anomalous? If you had no tables there, you would say, maybe not, maybe you're in the basketball court. But you see the context here, okay, there is a laptop, they are playing with the ball, that may be anomalous. So one thing that we need to be careful is anomalous is not necessarily suspicious. When you're doing surveillance, not everything that is anomalous, which is something that is different from normal, is suspicious. So what we're doing here is we just saying anomalous, not anomalous, different from normal or not. We don't know what's suspicious. Who knows what suspicious is the operator of the system. We are just filtering the data to the operator, make decisions. So we're not removing the human from the loop. So what we did here, we create a histogram of optical flow. This is a handcraft feature that we presented in CBGRAPH 2015. What we're doing is the previous descriptors, they just consider the orientation of the flow without taking into account the magnitude of the flow. The optical flow gives the velocity of the pixels in the image. So is this pixel moving fast or slowly? The previous work, they just, this pixel is moving towards that direction. When the pixel is moving, the person underneath the pixel is moving. That's the idea. So you get all this information, the pixels in the person, and you know the direction. If it's a direction that have not been seen before, it means it's anomalous, because people only go downstairs here, for example. At some point, the person start going upstairs. We say that is anomalous, because we never seen before. So what we never seen before, we say that is anomalous. I don't know the class, but I know that is something different from what I've seen. And they just did the orientation. So instead of just considering the direction the people are walking, we also consider the velocity, the speed of the people. So instead of creating histograms, I'll go quickly here, instead of creating a histograms of the orientation only, we create a histogram of the orientation, but also we split the histogram for the speed. So basically we have a matrix. Instead of a histogram, we have a matrix where you have each position of the matrix entails a specific orientation and a specific speed. So now I can differentiate if the person is running or walking. Before I only knew the orientation. Now I know the orientation and the speed. So it's an improvement over the previous features. So we got some by the time, and we got some nice results here. We improved the literature. Notes that this is only with handcraft features, because it was 2015. In this video, you can see when it's marked, it's an anomaly. So it's something that wasn't seen before. For example, this car crossing here, it's an anomaly, because there is no, it wasn't supposed to have a car there. And we know that beforehand. So we basically, you sit your camera there, watch the environment for a few days, then you start, you know the patterns that are supposed to happen, and then we test later if some pattern that wasn't supposed to happen, you have to mark here. For example, people are running their bike there, something like that. Okay, that was handcrafted features. So now with deep learning, we switched for deep learning, but instead of using, as I mentioned earlier, just add the images as inputs, we want to do some transformation before, instead of adding the frames as the input for the network, we want to do simple transformations that improve the quality of these models, and it avoids to have many parameters in the network. So basically here you have your scenario, you have the movement of the people, and you want to capture this spatial temporal information. Again, it goes back to optical flow. Now, optical flow, as I mentioned, it measures the speed and the orientation of each pixel. So here is what has been done. Before that, we had, instead of using deep learning, we have some mid-level representation to, you get your features, you extract features from interest points, then you have mid-level representations using bag of visual words, then you train a classifier. Basically all these phases here are merged now with CNN, so you just have one phase that you present your frames. It's going to learn the best features, it's going to learn the classifier. Basically, it learns the model that when you have a test, you just present it to the network again. Before our work, the common was to do this. You have two strings of, basically you have two networks. This first network, you code the appearance. Basically, you just stack the frames, a subset of frames, learn a network. And the second, instead of getting the appearance, you get the flow. So you have the movement in the y direction and x direction, and then you learn a new network specifically for this information. So basically, the second network is encoding the temporal information, and the first one is encoding the spatial information. Then you do a fusion here. So how can we improve this? How can we do a better, how can we pass richer information to the network? So here is the optical flow of that video. Here is the optical flow of each one. So what we do, we separate the magnitude from the orientation. So you saw in the previous slides, you have the appearance entering in one network, and in the second network, you have the X and Y of the optical flow. So what we do, we pick the X and Y, perform these two transformations, and then you have two richer information entering the network, which is the magnitude and the orientation. And that's it. We just changed this. We employ a nonlinear transformation in the XY, and we presented this result to the network. Just by doing this, we were able to improve the results. So basically, you compute the optical flow, and then you compute the magnitude. Now this would be the second flow, the temporal information being captured by the network. So we, as they did, computed the optical flow. Now we compute the magnitude and the orientation, and then we present it to the CNN with some data augmentation, which is usual in deep learning. Let's keep this. This is just the equations of the magnitude. Basically, magnitude is the magnitude of the gradient of the vector from the optical flow. The orientation is the orientation of that vector when you integrate x and y. As the results we test in UCF 101 and HMDB 51, which are the current data sets that people evaluate activity recognition. The first one has 101 activities, so this is different from anomaly. In anomaly, I don't have the label of activity. I know that is suspicious, abnormal or not. Here I want to classify among these 101 classes, and the second data set has 51 classes. And here's the results. This is our method, the MOS. We achieved better results in this baseline. And here we can see the confusion matrix by using our method and the other methods. By using our method, what we see here, it's hard to see from the back, but what we analyze from this confusion matrix is that when we make a mistake, we confuse classes that are semantic similar. So classes very similar. The previous method, when they make a mistake, they confuse classes that are very different. So the addition of this transformation to insert the magnitude and the orientation is able to increase the semantic level of the information by looking at these plots here. Here is the comparison with the literature. We compared with many methods, handcrafted methods. We are able to, in these two data sets, we are able to outperform all of them. These are handcrafted methods. We also compared to deep learning based methods. We are able to outperform all of them but one, this TSN. We don't outperform it. That's because they use a different architecture, network architecture, a more deeper architecture, and they perform their training in a much larger data set. So they are using outside data to perform their training. We don't do that. We use only the data from the data set to perform the training. So that's why these guys achieved better results. They're using more data to train. Everybody knows the problem of deep learning is to have data for performing training. Okay, so now enough of technical boring stuff. Let's go to more boring stuff, technical boring stuff, but now in ongoing projects we have there and some research opportunities, so open-end problems that we are looking for, we are looking after and we are interested on. The first is activity camera. As I mentioned before, you cannot cover the environment with few cameras and you cannot put many cameras in the environment because it's expensive. So how about using these PTZ cameras to cover the environment as you need? So if the person is walking around, let's follow that person. So we call this activity camera. It has two problems, which is control of the camera. How do you control the camera to follow a person? It seems trivial, but it's very hard because it has to be done in real time. And the coordination of the cameras. If you have multiple PTZ cameras, PTZ are those cameras that you can move automatically by software. You can pan, tilt, and zoom. If you have multiple of these, you have many people in the room, how you choose who to search? You want to maximize a criteria that could be increase the number of seconds that a face is visible for the camera, or you can increase the coverage. I want to see the face of everybody at least once in a minute, for example. So we are starting this in this area. Here is some results we have is just qualitative results. We see that the camera is moving towards the face of this person. This is inside the lab, so we have cameras mounted there. And also we have results from it's not results, they're example, from outside of the lab. So you can see the camera is following the person that is walking. So it's not doing zoom. Here you can see it's following, then once it finds the person, it zooms in the person. So this is the fixed camera that has a wide view of the environment, and this is the PTZ camera that keeps tracking the person and performing zoom. There are lots of open issues here. For example, how can one coordinate multiple cameras? Master slave. Master is the fixed camera, slave is the PTZ camera, so the master coordinates the PTZ camera. How do you coordinate multiple cameras? There are literature on that, but it's still not solved. And also how to reproduce the experiment, how to rerun the experiment to compare new methods with previous methods the problem is once you make a decision, you cannot go back. So you cannot rerun your experiment because it's being run in real time. So once you send a command to the camera, that's the command you send to the camera. How to re-execute this experiment? It's a hard problem. Another problem we're working is personal re-identification. Basically, you have a network of cameras. A person is walking here in one camera. The same person is walking in another camera. The challenge here is to say the person that walked here is the same as the one that walked in this second camera. So basically, what you're doing, you need to do a matching in different cameras, and that's a very challenging problem because the view is different. In one camera, the person is going to be front to the camera, the other one is the back, so you cannot rely on face information. And also, you have large camera networks. In the computer science department, we have 74 cameras installed that we have access to do this problem. So basically, you have to process all this data also, make the matchings. It's a scalability issue again. So what is open here? How can you run for many cameras? How to improve the appearance modeling, since in one camera you're seeing from front, another one is seen from back. The illumination of the cameras are different. One is in a closed space, another one is in an open space. So how to improve these models? How to use data fusion for this? How to get many information, for example, when I have the face, use the face. When I have the appearance, use the appearance. You can use the gait, the way the person walks to improve this information. Also, these days you have cell phones with sensors. You can use this information to use the sensors from the cell phone that you can identify the person by the way the person walks and throw here. So how to solve this problem is still an open issue. Another problem is the anomaly detection that I talked before. It's still an open problem when the camera is moving. How to do this? Because we learn the environment based on the scene you're seeing. If you move the camera to another place, how to solve this problem? You cannot rely on pixels anymore. You have to rely on high-level information. How can you learn in one environment, for example, here in this auditorium, and test in another auditorium? They have the same purpose. The room has the same purpose. So the activities here should be similar to activities in another place. So how to learn here and test in another place? This is also a scalability issue. How to improve data representation, as I mentioned before. Another problem we are working on is license plate recognition. This is a pretty controlled environment. It works well. But if you're in this environment here, you have a moving car, and you're trying to recognize the plate of this car in front of you. The camera is moving, the cars are moving, blur everywhere. So if you freeze one frame here and crop the plates, you don't see anything. You don't see anything here, you don't see anything here. Maybe if you integrate over time, you can get to this information. So this is an open problem. This is another example. The car is entering the parking lot. So it's stopped, but you cannot see the license plate. The door is going to open, the car is going to enter, but it's very hard to see the license. So it's solved. When you talk to people, they say, oh, it's solved problem. It's solved if you have a more controlled environment. If you are in this environment where cameras are moving, poor illumination, it doesn't work well. So how to handle this problem in moving cameras, how to model the blur in the license plates, how to recognize at night and at high speed. The car is running fast. Another problem is human recognition, human activity recognition. For example, the person walks in the room and the activity is being recognized here. The person sits, the person starts eating, the activities are being recognized. So there are many works on this, but there are still open ends to work on. For example, how to use multiple sources of information, sensors, based on sensors placed in the environment. For example, if you have a smart home, sensors that you carry, your cell phone, and cameras, both cameras in the environment as the GoPro in your head, for example. How to integrate all this information. Synchronization of all these devices. It looks like simple, but it's a terrible problem. You have data from sensors, you have data from cell phone, you have data from cameras, IP cameras, you have data from GoPro cameras. How to synchronize all this data? Otherwise, it doesn't make any sense to fuse this data if you don't have they're synchronized. It's also an open problem. More information. Can you use more information? For example, this information here. Is it working? Nowadays, we have very good results on pose estimation, which is this one. You can see the person walking here, and all the joints are being marked. And this works very well. This is a paper from this year, CVPR this year. How to use this information to improve the activity recognition, how to integrate more information on the process instead of looking at the video, at the whole video, looking into parts of people. And also deep learning. There are many open issues in deep learning that we are interested on. How to compact already trained models. For example, if you want to run your network in the cell phone, how to reduce the size of this model to fit in the memory and to be faster, how to seize the network, how to optimize the network architecture. Instead of spend 3 days sitting there and testing, okay, let's try 10 layers, 12 layers. Is it possible to do this automatically? We are trying to investigate this. How to represent videos with a small number of parameters, which is enrichment of the representation to be presented, to be used by the network. How can we learn incremental models for deep learning? So we have an initial training, then new data appears. How to incorporate this new data into pre-trained model. And how to perform data fusion using network multimodal data, for example, from sensors and from sensors and from videos. In biometrics, we want to use robust information, use sensor information to improve the results in the biometrics. Find new traits on biometrics, as I mentioned, that you can recognize well from the distance to be useful in surveillance. And the last problem we are interested, I think is the most important and is not appreciated in the community, is the surveillance systems. Because today everybody has solution for each problem, but nobody integrates those solutions to have a surveillance system. So we are interested on solving all these problems at once in a real scenarios. The only way is to building surveillance systems. So to conclude, I would like to acknowledge, I'd like to thank you, my students, the agencies, the companies that have been our partners, and thank you.
Well, thanks, William. That was really a tour de force, a fantastic review of the field and some of the really interesting problems. I'm curious, it's a lot of what you talked about in terms of surveillance related to almost like security types of applications, in the sense that those were the most challenging because they were typically in uncontrolled environments. We don't know what the perpetrator is potentially trying to do. So a bit of a philosophical question for you. On the other hand, there are many, and you showed some of this, applications where the environment is controlled. We know who the players are. Smart health monitoring, for example, things like that. In terms of the effort being invested by the community, how much work is actually being done in terms of security surveillance versus sort of so-called smart surveillance, where we're actually just trying to take care of people, we're just trying to do things that we know what we want to do. We're not, do you understand what I'm trying to get at? I'm wondering is it 90% of the people are looking at trying to identify terrorists, or is it that in fact there's a healthy number of people who are doing sort of more, I don't know, applications that are not focused on, say, security issues?
Yeah, it's more people do the case where it's more controlled. So, for example, healthcare, when you have elder people in the home, in a smart home, you know who the people are and you know the activities you're monitoring. So the methods in the literature are more suitable for this kind of application, because they don't try to handle these extreme cases. We have interest, but we have interest on this, but it's very hard. So we are also going with the literature, improving a little bit, but with the focus of having a whole system that could be useful for surveillance. I don't believe that it's going to be very easy to be able to run everything in real time and get the anomalous, all the types of anomalous events. But once you add this in a real system, if the operator can monitor one camera instead of two cameras, it's very helpful to them. So it's a step-by-step process. So I don't know if we're going to be able to run on those videos, the metro station video, in 10 years. It's a hard problem. But once you solve it for those extreme cases, you can apply to more controlled cases. Now, one project we have is for health, and basically you monitor people, and then you get a subset of these tasks to be solved. Then it is easier.
Thank you.
Thank you. One more question. Thanks, William, for your presentation. It was impressive work for us.
Thank you.
I was wondering if at this point the idea of person or environment behavior prediction is viable at this point of the research.
By prediction, you mean know what the person is doing is very hard in general, because then you go to activity recognition. You need to know what you're looking for beforehand. But anomaly detection, it's more feasible. So if you go into this surveillance part of the problems, it's better to go to anomaly detection than activity recognition, because you never see for example, you don't have training videos with hijacking. You don't have training videos with mug shots. So somebody's mugging somebody. It's very hard to get the training for this. So what you do is you learn the environment, you learn the activities that are normal, then everything that's not normal, you set a flag. Then somebody has to go there and review it. So it's more than this side, anomaly instead of activity recognition.
Okay, thank you.